So we've talked a little bit about latent heat already, but we've talked about it more in terms of a global energy transfer. Okay? It is energy that is transported in moisture-laden air masses. Water takes a lot of energy to turn from a liquid into a vapor, and when that vapor moves from one place to another, it takes all that energy with it, and then when it gets to the new area, it condenses and it releases that energy to the new area. Okay? While it's moving, it is latent heat. When it condenses back into liquid water, it becomes sensible heat. Okay? That is heat that we can sense. Right? Heat that results in a change in temperature and an increase in energy. Right? That's the context in which we've talked about latent heat. Now what we need to look at is the actual energy part of it, the numbers. Okay? What are we looking at in terms of how this happens, okay, and how much energy is being carried by this moisture. Okay? So what we're going to be looking at is, first off, what latent heat is, and then we're going to be looking at the heating curve of water, which is this diagram that you see here. Right? The heating curve of water tells us what happens to the temperature of water as you add energy to it. All right? So if we start at minus 25, what state is water generally in? Ice. Yeah, it's frozen, solid. Right? Its freezing point is 0 degrees Celsius. So at minus 25, I would have a block of ice. If I put it in a pot and turn on the burner, what will happen to the ice?
It will melt.
Okay, that's what everybody says. It'll melt. And you're right, eventually. But what temperature does it have to get to first? What temperature does ice melt at? 0. Okay, we all just go, it'll melt. Actually, first it'll warm up, and then it will melt. It doesn't take long for it to warm up, but it has to get to 0 before it will change state into a liquid. So that's what you're seeing on this diagram here. As I add energy, that's the x-axis, okay, I'm going to see an increase in temperature, right? So we start at minus 25, I add energy, and very quickly the temperature increases to 0. All right, once I get to 0, I continue to add energy. What happens to the temperature? Stays the same. So I'm adding heat, but the temperature isn't changing. What is changing? What's the ice doing right there at 0 degrees? Changing state. Changing from solid to liquid. During a state change, there is no temperature change. Thermal energy works a little bit differently than mechanical energy does. If I do work on an object, I change its mechanical energy. I can change both its potential energy and kinetic energy at the same time. Thermal energy doesn't work that way. If I add heat to something, I can change either its kinetic thermal energy, that is how fast the particles are moving, or I can change its potential thermal energy. That's its latent heat. Okay? That's what happens when its particles move away or closer to one another. So obviously, as a solid, particles are supposedly packed in very tight. Water is actually a little bit different, okay? Because water is a polar molecule. What does it actually do when it freezes? It expands. It's actually less dense, an exception, but still. Okay? The particles in a solid are usually quite rigid. Water has a crystalline structure, so the particles don't move very much as a solid. Okay? So they're kind of tightly packed or in a crystalline structure where they can't move. So they move a little bit, they move a little bit, they move a little bit, and then when I get to 0, the state changes, and the particles leave that crystalline structure and enter a fluid state, where they can now change places and move all over the place. Okay? Changes from solid to liquid. That's changing the potential energy of the material, in this case water. So anytime you make particles move further away from each other, or let them get closer to each other, you're changing the potential thermal energy of that material. Right? When those particles go back to a closer position, they'll release that energy. They'll release that latent heat that we've been talking about. Okay? So that's what happens when when we're releasing latent heat, is we're changing the state and we're getting particles to move either further away or closer together. Okay? Once we have a liquid, once the ice is all melted, and believe me, it doesn't change temperature until all the ice is melted. Okay? This is why we put ice in drinks. Okay? We put ice in drinks because it keeps them cold. It takes a whole bunch of energy to melt ice. And your drink will stay at around 0 degrees Celsius until all the ice is gone, and then it'll warm up. Okay? You guys have noticed that, right? As long as there's ice in your drink, it's cold. As soon as the ice is gone, it very quickly warms up. Okay? So it'll all stay the same temperature until all the ice is melted. Then if I continue adding heat, obviously the water is going to get hotter. Okay? So I add energy, the water will heat to 100 degrees Celsius. And what will happen at 100 degrees Celsius? It'll boil, right? Okay? And as it boils, it'll stay at 100 degrees Celsius. Okay? Liquid water, at least in standard conditions, 1 atmosphere of pressure, okay, will boil at 100 degrees Celsius, and it will stay boiling. It won't exist past 100 as a liquid. Okay? And eventually, once all the liquid has evaporated, I'll have all steam. Okay? And then if I continue to add heat, the steam will get hotter. Everybody with me on that? All right? So what part of this graph requires the most energy? Remember, the x-axis is how much heat we've added. So which part of this requires the most heat? Here. Right here? That's got the biggest temperature change, but which one uses the most heat? Yeah, this part. Okay? Changing water from a liquid to a gas requires more energy than almost all the other steps combined. Okay? Almost all the other steps combined don't add up. It's a little bit more, but it's almost more than all of them. Okay? Just to evaporate the water. It takes a ton of energy to change the latent heat of liquid water into vapor. All right, so there's 2 types of latent heat. There's the specific latent heat of fusion. That has to do with melting and freezing. Okay, so F for freezing. Okay, latent heat of fusion, that's melting and freezing. And then there's a latent heat of vaporization. That has to do with evaporation and condensation. Now, what we're hoping to be able to do here is, if they were to say you have 500 grams of water, or of ice, sorry, at minus 25, how much energy would you need to add to turn it into steam at 125 degrees Celsius? Okay. They might ask us to calculate that. Now you're probably looking at that and going, holy crap, that seems like that would be really hard. But in actual fact, you already know how to do 3 of the steps. That's E equals mc delta T from yesterday. Okay? 3 of the steps use that formula from yesterday. Okay? The other 2 use a very simple formula. All you got to do is calculate each step, add them all together. Okay? There's no manipulations. All you have to do is plug in numbers. Okay? A question like that would be probably an 8 or 10 mark question, and it requires no manipulation, just plugging in of numbers. So it's pretty easy, 8 or 10 marks. I probably wouldn't give you a 5-step problem on an exam. I might ask you, how much energy would it take to go from here to there? Okay, that would only be 3 steps. Okay, it'll take you less time. All right, so we're going to look at how that's going to work. All right, so the amount of heat required to melt 1 gram of a substance with no change in temperature. So we're looking at this part of the graph. Okay, that's where the latent heat of fusion comes in. Okay, I can't use E equals mc delta T for this part of the graph. Why not? There's no change in temperature. It'll tell me that requires no energy. Okay, well, the reason for that is this formula actually calculates the change in kinetic thermal energy. Okay? Because kinetic thermal energy has to do with how fast the particles are moving. And we measure that with temperature. Okay? So if I'm increasing the temperature of a material, I'm increasing how fast the particles are moving. If I've got a change in state occurring, like here and here, that's where I'm changing the potential thermal energy of a material. And I use a different formula for those two spots. Okay, so anywhere the temperature goes up, I'm increasing the kinetic thermal energy, and I would use this formula here. Okay, anywhere where the line is flat, we're going to go over the two formulas you used there. Okay, one sec here. All right, so the latent heat of fusion for water. So this would be the amount of energy required to melt 1 gram of water, or 1 gram of ice, sorry. To melt 1 gram of ice already at 0 degrees Celsius is 333 joules. Okay, how many of you have ever made a snowball with your bare hands? Okay, we've all done that, right? Your hands get pretty cold? They do, pretty quickly. And it's not because the snow is all that cold. The snow is not all that cold. Okay? Good snowball making snow is usually around 0 degrees Celsius already. It might be like -2 or -3, okay? But it's usually not all that cold. But as soon as I put it in my hand, it starts to melt. Okay? Every gram of water, and I want you to understand, a gram of water is 1 milliliter. Okay? So we're not talking about a huge amount of water here. But to melt 1 gram of ice into 1 gram of liquid water takes 333 joules of energy from your fingers. Okay? That's why they get so cold so fast. Okay? You grab onto something cold, especially if it's ice, okay, it's going to start to change the temperature of your hands very quickly, because second law of thermodynamics, it's going from hot, your hands, to the ice, cold. And it's going to start melting that ice. So very, very quickly, your hands get very, very cold. 333 joules lost for every gram of ice you melt. Okay. All right. So if I was going to calculate how much energy would be required to melt 3 grams of ice, I would use this formula. E equals m, which is mass in grams, times LF. This is LF. 333 joules per gram. You don't have to memorize that. It's on your formula sheet. Okay? It'll be on both the unit and final exam, because the final exam you'll get a fresh periodic table / formula sheet. Okay? All right, so if I want to calculate how much energy is required to melt 3 grams, I just substitute 3 in for m and multiply by 333. So it would be 999 joules. 3 grams of ice is not a lot. All right, everybody with me there? Okay, so that's how much energy is involved just to melt ice. That's why it takes so long for the snow to disappear. Or if we get, a really big Chinook, that's how much energy is in a Chinook. Okay? We get a lot of snow to melt. When we get a Chinook, there's a lot of energy in a Chinook. Okay? It takes a lot of energy to melt that snow, okay? and that's helping it. All right. Now, this part of the graph, the biggest part, okay, the most energy requiring part of the heating curve of water, vaporizing liquid water into water vapor. Okay? For that, we use the latent heat of vaporization, or LV, and that number is 2,260 joules per gram. So 1 milliliter of water evaporates into water vapor. That takes 2,260 joules of energy if it's already at 100 degrees Celsius. Okay? Can water evaporate if it's not at 100 degrees Celsius? It sure can. Okay? Water can evaporate off of you even if it's not at 100 degrees Celsius. Guys, if it took water being at 100 degrees Celsius to evaporate, Earth would be a pretty hellish place. Okay? I mean, how would you get water to evaporate from the ocean? The oceans would have to be boiling. Okay? They're not. Water can evaporate at a lower temperature. It doesn't boil, but it can evaporate, and it still takes 2,260 joules of energy to do that. Okay, this is how a few things work. If you go and work out, or it's a hot sunny day, what does your body do to keep you cool? Sweat. Okay. Sweat works like this. Your body gets covered in a thin film of moisture, and that moisture starts to evaporate. Where does it get the energy from? You. Yeah, in general. I mean, it might get a little bit from, moving air or something like that outside of you, but for the majority of it, it's coming from your body. So every milliliter of liquid sweat, okay, that evaporates off your body is going to take a little over 2,000 joules worth of heat energy with it. Okay? Can that cool you off pretty fast? Okay? If you get all sweaty and stand in front of a fan, you can feel chilled pretty quickly. Okay? It's one of the reasons why we say if it's wintertime, you're going outside, you should dress in layers, right? So that if you start getting warm, you can take layers off. If you get sweaty and then you stop doing whatever you're doing and you're not working as hard, okay, all that sweat that you put out is still going to evaporate. And now you're out in cold temperatures and you've got this sweat that has to evaporate. It's going to make you very cold. Okay? So what you want to do in the wintertime is as you feel yourself getting hot, you take layers off, okay, so that you don't get wet with your own sweat. Okay? And because that can cause you to get chilled later. All right, so does that mean then if you sweat a lot, you cool your body better? Because, I mean, everybody sweats different. Like some people perspire, right? They get just a little beads, okay? And it's not so bad. And then there's other people who have a puddle around them, okay? I know I played basketball with a guy in high school. Like, after, he would not warm up in his uniform because by the time warm-up was done, he could wring it out. Because you didn't want to play shirts and skins with that guy because he was just slimy. And he'd slide right off of him. Okay, some people just sweat lots. Okay? Doesn't mean they cool themselves any better. They just have really active sweat glands. Okay? Having more water on your body doesn't mean that you're going to lose more energy. Okay? It just means you sweat more. Right? Way back in the day, the Oilers had a goalie named Nikolai Habibulin. And this guy would lose like 10 pounds every game in sweat. Okay? He would, every time there was a stoppage in play, he's coming back to the bench for a new blocker, okay, and a new mitt, because they would be soaked, right? They actually caught on the crease cam one time. He had holes drilled in his skate bottoms, and they caught on the crease cam, sweat dripping out of his skates and onto the ice. This is why the Oilers were no good in a shootout. By the time shootout came along, the guy had lost 10 pounds, he was cramping up, he couldn't stay hydrated. Okay? Didn't mean he cooled himself any better. He just made more ice around the net. Okay? Because he would sweat so much. It doesn't make you better at cooling yourself. Okay? Actually, a very thin layer of perspiration is actually a bit more effective than having it running off of you. Right? That's why sometimes at like outdoor events they'll have those little misting stations, right, where the cool water just comes off in a mist. You walk under and you feel so much better because it evaporates really quickly. Is that making sense? All right, now, once the water evaporates, it's now holding this much thermal energy. If it goes to another place and condenses, what happens to this energy? It gets released. Okay, ever heard the expression, be careful with steam? Steam can burn you worse than water. Okay, it's true, and it's not because steam is hotter. Okay, obviously steam can be hotter than water, but the problem with steam is even if I have liquid water at 100 and steam at 100, steam is still going to burn me worse because it has more total thermal energy. Okay? Liquid water at 100 degrees is right here. It only has this much thermal energy. Steam at 100 degrees has this much thermal energy. Is that a lot more? Way more. Okay? So what happens is if steam hits your skin, not only is it at least 100 degrees Celsius, which could burn you, it's going to hit your skin and condense. And when it condenses, it releases all of that. Okay? That's why steam can burn you so much worse than liquid water. Okay? It's holding way more energy in it. All this potential thermal energy will be released. Does that make sense? All right, so the formula for calculating how much energy would be in this step right here is E equals m times LV. So the mass, whatever it is in grams, multiplied by 2,260 joules. Okay. Everybody with me there? I want you guys to copy that down. We're going to walk through this. This is the kind of problem that you might get for latent heat. Okay? No?
Sorry, I missed that. Number for the.
2,260 joules per gram.
Okay, what was that? 3,330.
333 is the latent heat of fusion. That's for melting and freezing. Okay, if you get a question like this one, where it's talking specifically about water, and it's talking about water changing state, okay, and in this case we're going from ice to steam, so we actually have two state changes, you've got a heating curve of water problem. Heating curve of water problems all have the same set of steps to solve, so they're very formulaic, okay? As long as you know the steps, they're super easy, they're just plugging in numbers. So the first step is to draw the heating curve of water, okay, which was the picture that we had right here. Okay, this is the heating curve of water. Right, so all I do is I draw that. Right, so there's a step, a flat, a step, a flat, and a step. Right, this would be 0 degrees where water melts. This would be 100 degrees where water boils. Okay, and these would be the places where water changes temperature. Everybody follow me there? Okay. Anywhere where water is changing temperature, whether it's ice, liquid water, or steam, we're changing the water's kinetic thermal energy. That means we use E equals mc delta T to calculate how much energy, because we have a temperature change. Okay, weird thing about water, and this is not true for most materials, but again, water is the exception to every rule. Ice, liquid water, and steam all have different specific heat capacities. Okay? And it's okay, you've got those heat capacities on your formula sheet. It's not something you have to memorize. Okay? But they each have a different C. Okay? Liquid water is 4.2, steam is 2.2, and ice is 2.116. Right? They all have a different specific heat capacity. Right? But that's the formula we would use to calculate those steps. Okay? To calculate how much energy is involved in this step is the formula we just learned. E equals m times LF. Okay? Where LF is that 333. And then for this part, it's E equals MLV. Okay, next step is to identify how many steps there are going to be in this problem. Okay, could be anywhere from 1 to 5. This one's going to be how many steps? 5. Yeah. Okay, I'm going to start with ice at minus 15, so that would be like right here. And I'm going to steam at 150, which would be the very top. Not all questions are going to have 5 steps. Sometimes you might be asked how much energy is required to take liquid water from 80 degrees to steam at 110. That would only have 3 steps. All right, so how do I know this has 5 steps? Anywhere the line changes direction is the end of one step and the start of another. So there's step 1, there's step 2, there's step 3, there's step 4, there's step 5. Now I've already done most of the legwork here. I also now know which formulas I have to use for each step. All right, so now I'm going to break this down into the steps we're going to have to do. Okay, in step 1, I'm going to be warming the ice from -15 to what temperature? 0. Okay, I mean that's what this part of the graph says, right? I'm going from -15 to the melting point of ice, which is 0 degrees Celsius. Okay, and the formula I'm supposed to use is E equals mc delta T. All right. We have 250 grams of ice. So that'll be 250 times, what's C? What did C stand for? Yeah. Heat capacity, right, which is like latent heat, but it's for kinetic. Okay, so C is the specific heat capacity. So I've got to look up what's the specific heat capacity of ice. It's 2.116 joules per gram. All right, multiplied by the temperature change. How much am I changing the temperature by? 15 degrees. There is the most common mistake. I'm only changing the ice right now. That means I'm going from -15 to 0. Ice does not exist beyond 0 degrees Celsius. But what I often get is people put in the entire change of temperature and they write 165. Okay? I'm not changing the ice. I'm not changing the ice's temperature by 165 degrees. I'm only changing the ice's temperature by 50 degrees. Does that make sense to everybody? Okay? Because that's a very common mistake. Only for each step. Right? So times 15. All right, step 2. So in step 2, I now have ice at 0 degrees Celsius. And I'm going to continue to add heat. What's the ice going to do? It's going to melt. All right. To calculate how much energy is required to melt ice, I use this formula. E equals m times the latent heat of fusion of water, 333. So m times LF. What's my mass? 250. Will it be 250 for every step? Yes. Okay? I can't create or destroy matter. If I started out with 250 grams of ice, I'm going to end with 250 grams of steam. Okay? I can't lose water molecules along the way here. All right? So 250 times 333. That's our LF. All right, in step 3, right? In step 3, or at the start of step 3, I have liquid water at 0 degrees Celsius, right? Because I've just finished melting all the ice. So now I have liquid water at 0 degrees Celsius, and I'm going to continue to add heat, so the temperature of the water is going to increase to 100 degrees Celsius. Anytime there's a temperature increase, I use the formula that has temperature change in it, mc delta T. Right? So 250, but now it's water. So the C is now different, because liquid water has a different heat capacity than ice does. Okay? The heat capacity of water is 4.2. And how much am I changing the temperature by? So I'm starting here with liquid water at 0, and I'm going to liquid water at 100. 100. Okay? I'm changing the temperature of the water by 100 degrees Celsius. At the beginning of step 4, I have liquid water at 100 degrees Celsius. I'm going to continue to add energy for quite a while. And that water is going to evaporate. It's going to boil off. Okay? So as it boils off, it's going to use a lot of energy. And that can be calculated by going mass times the latent heat of vaporization at 2,260 joules per gram that we were talking about before. Okay, and then step 5, I've now evaporated all the water. I have steam at 100 degrees Celsius. If I continue to add energy, the steam is going to get hotter, right? Since the temperature is going to change, I'm back to this. E equals mc delta T. Okay, so that's going to mean I take the mass, 250, and now I multiply by the specific heat capacity of steam, 2.02. And how much am I changing the temperature of the steam by? Sorry, 50 degrees, right? Going to 150. All right. So don't have to manipulate anything. We just have to plug in numbers. Now we got to calculate each one of these steps. So our first step. Step 1 was where we were heating the ice from minus 15 to 0. Okay, and so we're using E equals mc delta T, so that'll be 250 times the heat capacity of ice, 2.116, times 15 degrees, because we're only heating it from minus 15 to 0. All right, so that's 7,935 joules. Okay. Next step is calculate how much energy is required to melt the ice. Right? That was mass times 333, the latent heat of fusion of water. All right, 83,250 joules. What generally seems to take more energy? Changing temperature or changing state? Changing state, yeah. Changing the potential thermal energy of something generally takes more energy than changing the kinetic. All right. The next step is how much energy is required to heat the water from 0 to boiling. Okay, so from 0 to 100. So 250 times the specific heat capacity of water times 100 degrees Celsius. All right, that's going to take 105,000 joules. Then we got to calculate how much energy would be required to evaporate all that water. And this is going to be the biggest or most energy demanding part of this question. So that'll be 250 times LV, which is 2,260 joules per gram. So remember, that's how much energy it takes to evaporate 1 gram of water. 565,000 joules. Okay, that's more than the other 3 steps combined by a fair margin. And the last bit, how much energy is going to be required to heat the steam? right? So we got our mass times the specific heat of steam times the 50 degrees we're going to change the temperature by. So 250 times 2.02 times 50 degrees. All right, 25,250. All right, I've calculated the amount of energy for each individual step. What do I need to do with those numbers? Just add them all together, and that'll give me the total energy required to take 1 cup of ice from minus 15, so that would be like straight out of your freezer, okay? And boil it off and heat the steam another 50 degrees. Okay. All right, 786,435 joules. Most of which was required to do the evaporate. All right, now we went through that really slow, right? But there's not that much to one of these questions. It looks like a lot, okay? But in the end, all we did was draw the heating curve, identify how many steps, performed the steps, and added the steps together. Okay? We took our time because it was the first time we'd done one, but in the end, a question like this looks like a ton of work, but really isn't. Okay? There's nothing to really think about. It's just a matter of plug the numbers, plug the numbers. All right, questions on what we did there? All right, I want you guys to answer the first, let's say just the first 4 questions, and then we'll talk about the answers to those, and then we'll look at a few more problems to solve after that. Okay, so these ones will require you to write out a bit of a sentence, or a couple of sentences to explain. Okay, so I want you working on the first 4 here for the next little bit, and then we'll go through them together. So let's talk about the first few here. So for question number 1, we put ice, obviously, in drinks to keep them cold because once we put the ice in there, it can absorb energy. But its added benefit is that it can absorb energy without doing what? Right? Without heating up. I mean, it heats up to 0, but it doesn't heat up after that. Okay? It just continues to absorb energy from the drink, melting obviously, but not changing temperature. So while it might dilute the drink a little bit, right, it isn't allowing the drink to heat up anymore because it can absorb energy without changing temperature because it's changing state. All right, we talked about how sweat cools us off. Okay, as you get a layer of perspiration on your skin, it evaporates, takes 2,260 joules worth of energy to evaporate that water, so it will cool you off because the energy to evaporate it is coming from your body. The same thing happens as you get out of the shower. Okay? Get out of the shower, you've got a thin film of water on you, it starts to evaporate, you feel chilled. Okay? That's why sometimes you have those little heat lamps in the ceiling, okay, for when you get out of the shower. Right? Because obviously when you get out, the water that's on your skin is going to start to evaporate. All right, gardeners often spray their crops before a frost. This is especially true in Canada for apple orchards and vineyards. If there's going to be a hard frost, they don't want the fruit to freeze because then it will be useless. So they spray it so that there's a thin film of water on the fruit. Why will that prevent the fruit from freezing? What will the water do? If it gets below 0, what will the water that's sitting on the fruit do? Freeze. When water freezes, it gives off energy. Okay? It's going from liquid to solid. So it releases 333 joules of energy for every gram of water that changes back into ice. Where does most of that energy go? Into the fruit, which keeps it from freezing. Okay? That'll work if it's going to be, like not a super hard freeze. Like if it's going to drop to -2, -3, okay? That trick will work. It's going to get to be -10. You got to harvest that stuff or it's toast. All right, which is better at keeping food in a cooler cold? 10 kilograms of ice at 0 degrees Celsius or 10 kilograms of water at 0 degrees Celsius? This is a common sense question. When was the last time you saw somebody fill a cooler with water? And, I'll put all my food in there and I'm just going to fill it with water. Okay? Nobody does that. A, that's dumb because you get everything all wet. Okay? But it also isn't going to absorb as much energy. That water has already done the most important part of the heating curve in terms of being able to absorb water. Liquid water starts right there on the curve. Ice at 0 degrees starts here. It's got this whole section of the graph that it can absorb yet that water can't. So ice has a lower initial overall thermal energy and thus is capable of absorbing more heat and keeping your food and drinks cold for longer. Okay, everybody all right with that one? Yep. All right. I want you guys to try number 7. Okay. But we'll look at the first step of it together here. So we've got 0.1 kilograms of ice. How many grams is that? Not 10. 100. Okay? There's 1,000 grams in a kilogram, right? Kilo means 1,000. 1,000 meters in a kilometer, 1,000 grams in a kilogram. All right, so I've got 100 grams of ice at -20. So we said the first thing to do is draw the heating curve. Where on the heating curve am I starting? No? Right, at the bottom, -20. And it says, how much energy is required to melt this ice? All right, so where am I ending? Here or here? Yeah. Stopping right there. How many steps is that? Okay, so you got two steps, this step and this step. I'll give you a few minutes to see if you can figure out what those steps are, and then we'll look at that together. All right, so we said there would be two steps. Okay, this is step one, this is step two. Okay? In step one, I'm heating the ice from -20 to 0. So what formula am I going to use for that one? Right, I'm going to use E equals MC delta T because the temperature is changing in step one. Right, they told me the mass, it's 100 grams, times C, because this is ice, I use the heat capacity of ice, 2.116, and I multiply that by the temperature change. I'm going from -20 to 0. So that's 20 degrees. Right? Then in step two, I'm starting right here with ice at 0, and I'm going to water at 0. What formula do I use for that part of the graph? E equals MLF, right? Because I'm going to be melting the ice, and LF is latent heat of fusion. That's melting and freezing. So 100 grams, and the latent heat of fusion of water, 333 joules per gram. Again, you do not need to memorize these numbers. They are on your formula sheet, and if they're needed on a test, they'll be on the test as well. Okay. All right, so if we're punching in our numbers here, we'll have for step one, 100 times 2.116 times 20. So that's 4,232 joules. And then for this one here, we should have 33,300 joules. Right? Okay, so if I add those two together, my total should be 37,532. Everybody follow what I did there? I would say on a unit exam, you could expect to get a 3-step problem. That would probably be worth, let's say, 8 marks. Right? Here's where your marks would come from. You get 1 mark for drawing the heating curve of water and identifying your steps. Okay? You would get 2 marks for each step. So identifying the formula and putting in the right numbers and getting the answer. So that'd be 2 marks for each step, and then 1 mark for your final answer. Right? That'd be 8 marks for a question like that. Okay. Try number 8. That was an exam question a few years back. All right, so we're converting 0.05 kilograms. How much is that in grams? It's 50 grams. Okay, we're taking that much ice initially at -10. We're going to water at 80. Give you guys a few minutes on that. Okay, so let's start this one out here by drawing the heating curve. We're starting at -10, so down here, and we're headed for 80 degrees Celsius, which would be right about there. How many steps is that? 3. All right, I have to heat the ice from -10 to 0. That would be step 1. I have to melt the ice. That would be step 2. Then I have to heat the water, step 3. So what formula am I going to use in step 1 since I'm heating the ice? MC delta T. I'm changing the temperature of the ice in step 1. Okay. And so in step 1, that means I'm going to take my 50 grams, multiply it by the heat capacity of ice, and a temperature change of 10 degrees Celsius from -10 to 0. So 1,058 joules for step 1. All right, in step 2, what formula am I going to use there where I'm melting the ice? MLF. All right, still 50 grams, now times LF, which is 333. 16,650 joules. And then in step 3, I've got to heat the water from 0 to 80. So what formula will I use there? MC delta T. So 50 times the heat capacity of water now, 4.2, and I'm changing the temperature by 80 degrees. All right, 16,800 joules. All right, add all those together, and we've got our final answer of 34,508. Okay, are those making sense? Got a couple videos I'm going to show you here on the